The topic is linear inequalities and problem solving. Uh, a quick bit of definition. An inequality is a statement that contains the symbols less than, greater than, less than or equal to, or greater than or equal to. In fact, we could add the not equals sign to that. So an example of an equation would be x equals 3. An example of an inequality would be x is greater than 3. An example of an equation would be 12 equals 7 minus 3y. An example of an inequality is 12 less than or equal to 7 minus 3y. So instead of an equal sign, there's one of our inequality symbols there instead. We solve inequalities the same way that we solve equations, just with one minor tweak. But that is why at this point you do need to know how to solve an equation, because we do the same thing with inequalities. If you need to brush up on solving equations, we will go into enough detail that the solving of inequalities should refresh your memory. The first objective in this topic is to use interval notation. Now, we use interval notation as a way of interpreting or giving the data from a graphed solution. Now, a solution of an inequality is a value of the variable that makes the inequality a true statement, just like the solution of an equation makes the equality a true statement. The solution set of an inequality is the set of all solutions. That's where things are drastically different from equations. Equations usually have one answer. Very rarely do they have a solution of all real numbers. Normally, we solve a linear equation, we get one specific answer. But when we're solving inequalities, we're saying things like is less than or is greater than. There are multiple solutions that satisfy and make it true. The solution set combines all of those. So we might, instead of saying x equals 3, say x is greater than 3. And then we can throw that solution on a number line. And it is the number line representation, the graphed solution, that kind of gives us the go-between between set notation and interval notation. In previous math classes, you may have been familiar with using open circles to represent not equal to the point and filled in circles to represent equals to the point. You can still do that, but it's a lot easier in getting to interval notation if instead of open circles, you use parentheses, and instead of filled in circles, you use square brackets. Parentheses go with the open circle, parentheses go with less than or greater than. You can see there in set notation, this would represent x is less than a. This would represent x is greater than a. The shading on the graph is the variable x. So here, everything is shaded less than to the left of a. Here, everything is shaded to the right of greater than a. But because a itself has a parenthesis, that means we're not including that point. And we're not including that point a because it doesn't say or equal to in either the strictly less than or the strictly greater than. What interval notation is basically a snapshot of what's on that graph but in an interval where the first item represents the leftmost point and the right indicates the rightmost point. So here, as far left as we go on the graph, is the all the way to the left arrow. In other words, negative infinity is involved. So the leftmost point in the interval is negative infinity. Now, to remind you, I kind of misspoke there. Negative infinity is not a point, so it's not the leftmost point, but it is the leftmost consideration. Negative infinity is just the idea of on and on and on forever to the left in the negative direction. It never stops. It's never going to reach a thing that it says is negative infinity and we end here. And that's why negative infinity will always have a parenthesis, because we can never be equal to negative infinity. It's not a thing that we can be equal to. It's an idea. It's a concept. And then the rightmost consideration is the point A, but we had a parenthesis there. We can just copy that parenthesis over. The parenthesis means we're not including A. So this is the interval notation to represent X is less than A, or this graph. Similarly, the greater than A graph. The leftmost consideration is the point A, but we are not including it. It is an open parenthesis. So we have the parenthesis with the A on the left. And the rightmost consideration is on and on and on forever in the right direction, in the positive direction. The rightmost consideration would be infinity, which again is never something we can be equal to. It's an idea. It's the concept of going right, going positive forever and ever and ever without stopping ever. So since we're never there at infinity, it can never have a square bracket. So no square brackets next to negative infinity, no square brackets next to positive infinity. Also, negative infinity will always ever only be the left, because that's where it exists on the graph. It exists all the way to the left. Likewise, positive infinity can only ever show up on the right of interval notation, because positive infinity is all the way to the right on the graph. So you're never going to have an infinity in the first position. You're never going to have a negative infinity in the second position. Again, the two things in the interval represent on the left, the leftmost consideration, on the right, the rightmost consideration. If we bring the or equal to into it, then the graph of X is less than or equal to A, which again, you might know as a filled in circle at A as opposed to an open circle, we can use a square bracket to indicate that the or equal to includes A. Once again, the leftmost consideration is negative infinity. Negative infinity always travels with a parenthesis. Even in cases like this, where the A has a square bracket, we are allowed to mix parentheses with square brackets. The greater than or equal to A, square bracket at A, and then everything greater than is shaded. The leftmost consideration is A. A is traveling with a square bracket because of the or equal to. The rightmost consideration is positive infinity, and positive infinity always travels with a parenthesis because we can never be equal to an infinity. Now, these were all the way to the left, all the way to the right. We also have to consider betweenness. So let's say we had X is between A and B, or A is less than X is less than B, where X is the stuff between A and B. Well, since to the left we have no or equal to, and on the right we have no or equal to, those would be parentheses. So a parenthesis at A a parenthesis at B. And the shading is the X. It's the stuff in between A and B. We translate this directly to interval notation. We like the betweens. The betweens are easy to write. We don't have to think about infinities. It starts with a parenthesis at A. It ends with a parenthesis at B. Parenthesis with A, parenthesis with B. If both left and right had or equal to's, then we use square brackets. So square bracket at A, square bracket at B, and the X is everything between. The interval notation follows square bracket at A, square bracket at B. And we could have mix and match. No or equal to on the left, so the A gets a parenthesis. Yes or equal to on the right, the B gets a square bracket. Parenthesis at A, square bracket at B, parenthesis at A, square bracket at B. Or maybe the A gets the or equal to, and the B doesn't get the or equal to. That's a square bracket at A and a parenthesis at B. Square bracket at A, parenthesis at B. And then in those cases where all real numbers are a solution, that's the entire number line. The leftmost consideration is negative infinity. The rightmost consideration is positive infinity. And here, even though we're including everything possible on the number line, we still don't use square brackets because the infinities don't take square brackets. This just means all the way to the left forever and all the way to the right forever. Forever and ever, never stopping. Before moving on, I do want to point out that these are all less than symbols. Between can only be less than and less than or equal to. Between cannot have greater than. You can't say A is greater than X is greater than B. Why? Because the order from left to right matters. And less than is always on the less than is always on the left side. So to write it, A is less than X is less than B, that makes sense. X would be between A and B, A on the left, B on the right. You can't put an X in between with greater than signs. It just does not work that way. Likewise, interval notation is always read left to right. Leftmost, rightmost. I'm sure that in your entire math career, this is not the first time you've seen points on a number line. And maybe you've seen before now that there can be a difference between a filled in point and an open, an unfilled point. If I shade everything to the right, and notice when I'm shading, when I get to the end, I fill in the arrow tip as well to indicate that the shading would continue forever in that direction. The shading is X. The shading is your variable, okay? So if we're looking for X here, X is everything to the right of 5. It's everything greater than 5. X is greater than 5.
And when we have the point filled in like this, that actually means greater than or equal to. The one that's not filled in, that's just normal greater than. It means that 5 would not be a solution. The fact that 5 is an open circle is showing us specifically 5 is not shaded. If 5 was shaded, if we could be equal to 5, then the 5 would be filled in. We could be equal to 5. So here, x is everything greater than 5, but not equal to. The shading is x. X is greater than, but not equal to 5. So maybe you've seen filled in an open circle before, but what I'm here today to tell you is that filled in circle can also be represented with a square bracket facing the direction of the shading, so that this would be a left, an opening bracket, and then this is the inside stuff. And the open point, that one can be written as a parenthesis. Again, facing the direction of the shading. The shading would be inside this open parenthesis. That's the starting point. So let's think about this square bracket, this parenthesis. And square bracket will go the other direction. So this, the shading is everything less than -2. X is less than -2. It's not equal to because it's a parenthesis and not a square bracket. Here, the shading is everything less than 5. The shading is X. X is everything less than, 3, not 5. The shading is everything less than 3. X is everything less than 3. X is less than 3, but it's also possibly equal to 3 because this is a square bracket. Square brackets are the or equal to. So why am I making a big deal of showing parenthesis and square bracket when we already have a perfectly good open and closed circle system? Well, it has to do with this thing I said I'd show you, this interval notation. Let's say we had 2 is less than x is less than or equal to 7. On a number line, if we just used our open circles and closed circles, we would have an open circle at 2. We would have a filled in closed circle at 7, and X, the shading, would be everything in between. But not equal to the 2. Yes, possibly equal to the 7. If we did it with our new symbols, 2 and 7, a parenthesis and a square bracket. I'm going to copy this down here. A parenthesis and a square bracket at 2 and 7. Filling in everything here. This shows us directly that we have an answer, the interval from 2 to 7 with a parenthesis on the left and a square bracket on the right. This is the answer in interval notation. And this is standard or inequality notation. We can put inequality notation into set builder notation. What is set builder notation? Well, this uses the braces inside braces, the set of all x such that vertical bar x is between 2 and 7. So the inequality isn't a set itself. The inequality can be used in a set, in set builder notation. Interval notation, that is a set. I underlined that twice and the emphasis got lost. There we go. That is a set. So this is why we use interval notation a lot in math. It is a shortcut way of delivering this same information about a set with just endpoints. It gives the left endpoint, it gives the right endpoint, and then whether it's a parenthesis or a square bracket tells us if we include or don't include the endpoints. So you might have noticed I was doing graph examples that were just x is greater than, x is less than. And when I jumped to showing this, I went to a compound inequality. I went to one that had two numbers. And the reason I did that is because it was easier as a first example to do one like this. What do we do when there is only one endpoint, though? So I was showing something like this. This is x is greater than 3. I can see the first endpoint is a 3 because it's an opening parenthesis. But what do I put here? I don't have an endpoint because it goes on and on forever. Well, going on and on forever in the positive direction is the concept of infinity. And infinity always has a parenthesis, no matter what is over here. So if this was a 4 and it had a square bracket and it goes this way on and on forever, the square bracket goes with the 4, but the infinity always a parenthesis. And this would be x greater than or equal to 4. Or in set builder notation, the set of all x such that x is greater than or equal to 4. Inequality, set builder notation down here. But what we're going to use most often, interval. notation. If we had a number line with everything shaded, that would be going to infinity on both ends. Oops. That would be all real numbers. And this negative infinity, that's what we use for infinity on the left side, going in the negative direction forever. So this here, we would have a closing endpoint, the second point of -2. It would have a square bracket with it. But since it's on and on forever to the negative direction, it's going to begin with a negative infinity. Negative infinity always takes a parenthesis. Let's do another compound. If in set builder notation we are given the set of all x such that x is between -4 and 2, including the 2, what would this be on the number line? What would this be in interval notation? Well, the number line between is always leftmost value here, rightmost value here. We are not including the -4. We are including the 2. And I like it with the parenthesis and the square bracket, so we can jump straight to parenthesis, square bracket, -4 and 2. So there's interval notation. The interval from -4 to 2. This interval is a set.
The second objective in this topic, solve linear inequalities using the addition property. So again, I mentioned that this is going to be no different than solving equations. There's just going to be a little extra step.
So if we had the simple equation x plus 4 equals 0, how would we solve it? We want to get the x by itself, so we need to undo adding 4. We undo adding 4 with subtracting 4. Whatever we do on one side, we do on the other. It leaves us with just x on the left, and then 0 minus 4 is -4 on the right. If we wanted to express our answer as a set, it would be the set containing our answer, one number, -4. Solving an inequality is pretty much exactly the same as solving an equation. And I say pretty much because there is one important difference, but that difference doesn't come into play here. So let's say instead of equals, it was less than or equal to. X plus 4 is less than or equal to 0. You do the same thing, and you get the answer x is less than or equal to -4. Not bad. If you can solve equations right off the bat, you can solve 90% of inequalities. And I pulled that number out of thin air. No one ever has real percentages when they say that. What someone means when they say you can solve 98% of problems using that, they mean most. Great many most. So what's the special rule? What are the ones that we can't solve like that?
The third objective in this topic. Solve linear inequalities using the multiplication and addition properties. So not just the addition property, now also the multiplication property.
The rule comes into effect when you multiply by or divide by a negative. The word by is very important here. It doesn't mean any multiplication or division involving a negative. It is only when you have something and you're taking what is there and multiplying it by a negative number, or you are taking what is already there and dividing that by a negative number. That first number can be positive or negative, doesn't matter. The rule only kicks in if you are multiplying by a negative or dividing by a negative. And here's what happens. If you have that, you switch it to that. If you have that, you switch it to that. It is laughably easy if you can already solve equations. So if at this point you're not having any struggles with solving equations, if you are consistently getting the right answers, then all you're going to have to watch out for here is multiplying by a negative, dividing by a negative. And it's not going to be in every problem, but we will do a lot of problems where it does happen because those are the more interesting ones. But every problem is not going to have a flip. This one will. Let's say we have negative 6x plus 4 is less than 34. Well, let's pretend it was equals 34, and let's not do anything differently until we get to a step where we might multiply or divide by a negative number. Okay, so we want to get the x by itself, which means we want to get the 6x by itself, the negative 6x. Well, I can go ahead and subtract 4 from both sides because I want to keep it balanced. That leaves me with negative 6x on the left. Subtracting 4, that's not multiplying or dividing by a negative. So keep the sign like it is. 34 minus 4 is 30. I want to get the x by itself. I'm going to divide by negative 6. Warning, warning, danger, Will Robinson. I was going to say that's an old reference, but by golly, there is a remake, so it could be a more recent reference if you're danger. We are left with x on the left, but since we are dividing by a negative 6, the less than becomes greater than. Positive 30 divided by negative 6. Positive divided by negative is negative. 30 divided by 6 is 5. So the solution to this inequality is x greater than negative 5. On a number line, that means we would be at negative 5. There's no or equal to, so it's a parenthesis. And we want to graph greater than. So it's an open parenthesis with the shading to the right. Our answer in interval notation, we can see from that would be a parenthesis at negative 5, and it goes to infinity. Infinity always takes a parenthesis. So the answer in interval notation, parenthesis, negative 5, comma, infinity, parenthesis. Let's do another. Negative 5t minus 6 is greater than or equal to 24. Let's not do anything differently than normal solving of a linear equation until we run into a step, which may or may not happen, where we multiply by a negative or divide by a negative. To get the t by itself, we've got to get the negative 5t by itself. We've got to add 6 to both sides. Leaves us with negative 5t on the left. Leaves us with positive 30 on the right. Adding 6 is not multiplying or dividing by a negative. The inequality symbol does not change. Here, we are going to divide both sides by negative 5. Danger, Will Robinson. Switch the inequality sign. Positive 30 divided by negative 5 is negative 6. So t is less than or equal to negative 6 on a number line. We have negative 6. The or equal to means a square bracket. And since we want less than or equal to negative 6, it's going to point off to the left. And there's all of our shading. From here, we can see that our interval notation, we're going to start with negative infinity. We're going to end with a square bracket at negative 6. Comma separates. So our interval notation for t less than or equal to negative 6 is going to be parenthesis, negative infinity, comma, negative 6, square bracket. Let's complicate the inequality a bit. Let's take a look at negative 6 times the quantity x minus 3 is greater than or equal to 2 minus 2 times the quantity x minus 8. So again, we are going to treat it like it said equals unless we come to a step where we are multiplying by a negative or dividing by a negative, in which case the inequality sign flips. So with parentheses, what do we do first? Well, in an equation, we distribute to clear the parentheses. And that is what we do here. We're going to distribute the negative 6. Over here, we'll distribute the negative 2. Negative 6 times x is negative 6x. Negative 6 times negative 3, positive 18. On the other side, distributing the negative 2, bringing down the positive 2, and this will be greater than or equal to. There's no risk of us doing anything here. You might be saying, wait a minute, you're dividing this side by a negative, or sorry, multiplying this side by negative, and you're multiplying this side by a negative. Isn't that the special rule? No. These negatives already exist here. In the other problems, it's the steps of undoing everything. If we're multiplying by a negative in the problem, we will divide to get rid of it. But here, we're not getting rid of the negative 6. We're getting rid of the parentheses. And we're not actually multiplying the same thing on both sides. So this isn't what we mean by multiplying both sides by a negative number. Bring down our 2. Negative 2 times x is negative 2x. Negative 2 times negative 8 is positive 16. Yes, I will show an example of what we do mean by multiplying by a negative number after this one, because we've been doing dividing. So I will show one that clears up what multiplying both sides by a negative would look like. In the meantime, let's finish this one. Simplify by combining like terms on both sides. Nothing to combine on the left. On the right, positive 2 plus 16 is positive 18 minus 2x. I'm going to go ahead and add the 2x to both sides. Negative 6x plus 2x is negative 4x plus 18. If I subtract 18 from both sides, I get negative 4x is greater than or equal to 0. And let me write this over here. From negative 4x greater than or equal to 0, if I divide both sides by negative 4, I get x is less than or equal to 0. Got to flip that sign because we divided both sides by negative 4 in the process of solving. On a number line, if this is 0, less than or equal to 0 would look like that with a square bracket, which means our answer would be negative infinity to 0 with a square bracket on the 0. So just real quick to knock out that one I promised you before we do another one just like this. Something where we'll end up multiplying both sides by a negative number could look like this. T over negative 3 is less than 1. Here we would need to undo dividing by negative 3. We would do that by multiplying by negative 3. And here we're multiplying both sides by negative 3 to undo division. And that switches the sign. 1 times negative 3 is negative 3. Hopefully by now we're getting used to putting our answers in interval notation and getting that interval notation from graphing. Let's do another one with all the parentheses. 5 times 3x plus 1 is less than 4 times 5x minus 5. Distribute. 15x plus 5 is less than 20x minus 20. Going to subtract 20x from both sides. That leaves me with negative 5x plus 5 is less than negative 20. I'm going to subtract 5 from both sides. negative 5x is less than negative 25. And from there, which I'll move up here, I'm going to divide both sides by negative 5. Leaves me with x is greater than, because that flips the sign. Negative divided by negative is positive. 25 divided by 5 is 5. 5 to infinity inside parentheses. Okay, let's throw in some work with fractions here. X plus 1 over 3 minus 2x minus 4 over 6 is less than or equal to negative x over 2. Now, here, we can go ahead and multiply both sides by the least common denominator. And in this case, that's going to be 6. So if we look at our multiple list for 2, 3, and 6, six is the first number that shows up in all 3 of the lists. That means that 6 is the least common denominator of 2, 3, and 6 fractions with those numbers in the bottom. Why am I doing this? I'm doing this because it's going to get rid of the fractions. So notice, multiplying both sides means that the 6 gets distributed to both of these terms. So it's like having a 6 times the x plus 1, and all of that's over 3. It's like having a 6 times the 2x minus 4. All of that's over 6. And here, it's like having a negative 6x over 2 instead of just an x over 2. The 6 gets multiplied by that fraction. How is this helpful? Like I said, it's going to get rid of the fractions for us, because 6 over 3, that's just 2. And then 6 over 6, that cancels. So that's minus the entire 2x minus 4. Very important to keep that in parentheses because it is subtracting that entire thing, which means in the next step, we're going to have to be sure to distribute that negative. Less than or equal to negative 6 over 2. That's negative 3x. And look at that. The fractions are gone. If I keep simplifying, I'll get rid of the parentheses next. 2x plus 2. Distribute to get that negative through there. Negative 2x plus 4. The opposite of the negative is positive. Less than or equal to negative 3x. If I combine like terms on the left, 2x minus 2x, those cancel each other out. 2 plus 4 is 6. less than or equal to negative 3x. When we finish this up, 6 less than or equal to negative 3x, we see we're going to have to divide both sides by negative 3, which is going to flip the sign from a less than or equal to a greater than or equal to. 6 divided by negative 3 is negative 2. We're just left with the x there. Be super careful. This one ended up with our x on the right. This would be the same as x is less than or equal to negative 2. So right now, don't ask, why did it flip back? It didn't flip back. Here, we switched it, but the left side stayed the left side and the right side stayed the right side. Here, we're switching the whole thing. The left side comes from the right side. The right side comes from the left side. And then the little point stays with the x. The little point stays with the x. Pac-Man's mouth opens towards the negative 2. So on a number line, this would actually be to the left. Negative infinity to negative 2 with a square bracket. Let's go ahead and do another like this one. M minus 4 over 2 minus 3m plus 4 over 10 is greater than negative 3m over 5. The LCD, the least common multiple of 2, 5, and 10, that's going to be 10. I'm going to go ahead and multiply both sides by 10 so that I can get rid of the fraction. So this would be 10 times m minus 4 all over 2 minus 10 times 3m plus 4 over 10 is greater than, this is going to be negative 3 times 10, negative 30m over 5. The 10s cancel there. Here, 10 over 2 is 5 of these m minus 4s. And we're subtracting, in parentheses, the entire 3m plus 4. And then negative 30 divided by 5 is negative 6m. Distribute. 5m minus 20 minus 3m minus 4 greater than negative 6m. I'm going to go ahead and erase the top of this problem to give myself more room to work for now. I'm going to recopy this line exactly with no changes. 5m minus 20 minus 3m minus 4. This is, again, just so I have the room. You don't need to write this a second time. You can obviously just keep going. It's minus 3m. 5m minus 3m would be 2m. Negative 20 minus 4 would be negative 24. Less than minus 6m. I'm going to do this two ways. So there goes the rest of the middle. Because I'm going to do this two different ways to show you that there is a way where we don't flip here. So two different ways. You don't have to do both, but I'm going to show we get the same answer either way. So I'm rewriting this line two ways. First, I'm going to do it like we did the last problem. Since I can get this all done in one step by subtracting the m's to the right, I'll go ahead and do that. If I subtract 2m from both sides, negative 24 would be greater than negative 8m. And then I would divide both sides by negative 8. Negative divided by negative is positive 3. But since I did divide both sides by a negative, the inequality sign gets flipped from a greater than to a less than. We get 3 is less than m. To help me graph it properly, I'll switch the whole thing around so that the m goes over here and the 3 goes over there. And then the big side stays with the m and the little point stays with the 3. So this would be m is greater than 3. No or equal to 3 to infinity would be the answer. What if I always, no matter what, wanted to do every problem by taking the variables to the left and the constants to the right? In other words, what if I did do plus 6m as the step here? That'd be okay. There's nothing wrong with that. Be careful though, because now everything is on the left. 8m minus 24 is greater than what? 6m minus, or negative 6m plus 6m, those cancel away completely. 0m on the right. Leaving the m's on the left, I would then go ahead and add 24 to both sides. And then look at that. 8m is greater than 24. No multiplying or dividing by a negative going on here. Just dividing by 8. M is greater than negative 3. Will you look at that? Same answer. So same graph, same interval notation. So either way, we get m is greater than 3 here.
The fourth objective in this topic is solving problems modeled by linear inequalities. So here's an example. You are having a catered event. You can spend at most $1,200. The setup fee is $250 plus $15 per person. Find the greatest number of people that can be invited and still stay within the budget. So here we can spend at most $1,200. We're looking for the greatest number of people that can be invited. The unknown is number of people. So let's let X represent the number of people. The cost would be the setup fee plus the cost per person times the number of people. The $250 plus the $15 times X. And that would be at most 1,200. That means it can be 1,200. It can be equal to, or it can be less. It just can't be more. So we set that up and say that that is less than or equal to 1,200. 250 plus 15x is less than or equal to 1,200. So we take our inequality that we've set up and we go to solve it. We want to get the x by itself, which means we want to get the 15x by itself, which means we need to get rid of adding a positive 250. We get rid of adding 250 by subtracting 250. And when we subtract 250 from both sides, that leaves us with just the 15x on the left, and that gives us 950 on the right. We want to get the x by itself. We want to get rid of multiplying by 15. That means we are dividing both sides by 15. And when we do that, we are left with x on the left, and then 950 divided by 15 gives us about 63.3 on the right. We want the greatest number of people that can be invited and still stay within the budget. So this wouldn't be rounded up to 64, even if that was 0.5 or greater, because we need to be less than the 63.3. Therefore, the greatest number of people that can be invited and still stay within the budget is 63. So 63 or less to stay within the budget. And that is it for this topic.